So good morning my dear students. So today's class, this is our lecture 5. So in today's class we are going to see about compressors. So that is about reciprocating compressor and centrifugal compressors. Okay, so you can see the terms which are related to this reciprocating and this centrifugal compressors, and then the problems. So how can you work out the problems that are given for this GATE exams? So we can see the problems which are related to that, and then we can see an overall view of all the chapters that we have discussed so far. Okay, so in this class we are going to see about this compressors, especially on compressors, that is especially on reciprocating and centrifugal compressors. So in this, so you can see the analysis of cycle, this reciprocating air compressor cycle. So you can see that the indicated work per cycle, so it is the area under the PV diagram. So you know that the PV diagram is there. It is the area under this PV diagram. So 1 to 2. So which represents the net or the indicated work done on the air per cycle. So it represents the net or the indicated work done on the air per cycle. So the indicated work per cycle here, so it will give you the area A, B, C, D minus the area 1, 2, 3, 4, 1. So from this diagram, you can see that area A, B, C and D minus this 1, 2, 3, 4, 1. So when you write, so this equation, that is A, B, C, D will be equal to this area 1, 2, 3, 4, 1. So that is equal to area under 1 to 2 plus area under 2 to 3 minus this area under 4 to 1. So you can see that here, so you have to subtract this area. So when you subtract this area, so you will get this total area. So that will be the work done. So the total area will be the work done. Okay, so that area A, B, C, D will be equal to area 1, 2, 3, 4, 1. So that is equal to the area under 1 to 2. So that is if it is 1 to 2, so area under 1 to 2 plus area under 2 to 3, this is 3, and area under 4 to 1. Okay, so the total, this total area will be equal to this indicated work per cycle. So if you take like this, so this will be a rectangle and this will be a triangle. So add these two, you will get the total area. So if you write like this and find the total work, so you can see that the formula is W is equal to N by N minus 1 into P2V2 minus P1V1. Okay, so the indicated work per cycle will be equal to, so N by N minus 1, you can take this PV out, PV is equal to MRT, so M into R, so T2 minus T1. So when this is a polytrophic process, you can see that N by N minus 1 into P1V1, so you take P1V1 out of this, so P1V1 divided by P2V2 by P1V1 minus 1. So you will get like this. So you can see that, so you can take that P1V1 already out of this. So you can see that, so P2, what is the relation for this P2 by P1 or V2 by V1? So when you subtract, so when you find this V2 by V1 in terms of this P2 by P1, and when you simplify this, you will get the value P2 by P1 whole power N minus 1 by N. So use the PVT relation. So for polytrophic process, suppose if it is P1 by P2, so that is whole power 1 by gamma is equal to V2 by V1. So the process is polytrophic process. So you will get P1 by P2 will be equal to V2 by V1 whole power N. So you substitute that, so this one for V2 by V1, so in this relation, so you will get the value, so you interchange the numerator and denominators. So P2 by P1 whole power 1 by N, that is equal to V1 by V2, so whole power N. Okay, so you can get like this. So substitute that value here for V1 by V2 or V2 by V1 here. So you simplify it, you will get the value of this P2 by P1 whole power N minus 1 by N minus 1. So this will be equal to, so this equation is arrived from this equation. Okay, so that is W is equal to n by n minus 1 into P2 V2 minus P1 V1. So take this term out of this. So you have taken this one out of this. So P2 V2 divided by P1 V1 minus P1 V1 by P1 V1 will be equal to 1. So you will get this. So simplifying the substituting the value for V2 by V1 in terms of P2 by P1 or in terms of P. So you will get the value P2 by P1 whole power n minus 1 by n. So this is the equation for this indicated work per cycle. Okay, so you have to know. So there is here in case of compressors, you have to know the value for, that is the formula for the work done, then indicated power, so then isothermal efficiency, adiabatic efficiency and polytrophic efficiency. You should know, you should be thorough with the formulas that are given in the syllabus. Okay, so right, so indicated power. So the indicated power is the work done on the air per unit time. So the mass flow per unit time, that is m dot, is often used to compute the work done per time. So or the indicated power. So n by n minus 1 into mr into T2 minus T1 refers to the indicated power. So then mechanical efficiency. Okay, so it is the ratio of indicated power to the shaft power. So which is, shaft power is nothing but the sum of indicated and the indicated power and the friction power. Okay, so shaft power is the power that is supplied by the electric motor to the compressor. Electric motor to the compressor. So motor efficiency, it is the ratio of shaft power to the input power, and input power is the electric power that is applied to the electric motor. So why I am saying all this? So you should know the, so suppose you may get a problem which is related to this motor efficiency in this reciprocating air compressor. So you have to be thorough with what is the formula for this motor efficiency. So then how that motor efficiency is determined. So it is the ratio of shaft power to the input power. Input power is the electric power that is supplied to the electric motor. Okay, so then compressor with clearance volume. So you can see here. So in the previous case, we have seen that there is no clearance volume. So and you got this that A, B, C, D, and from that you find the total area. Then you determine the value of this work done, that is indicated power, indicated work per cycle. So that is n by n minus 1 into P1 V1. Inside the bracket you got P2 by P1 whole power n minus 1 by n minus 1. So you got that. But here, so in this case, so some clearance is provided. You can see that a clearance is not this. So a clearance is provided. Okay, so this volume is the clearance volume, and here it is the actual amount of air that is taken in, so that is inside the cylinder. So that is called as effective swept volume. So that is from 4 to 1. So this is the air amount of air that is sucked in by this compressor. So this the amount, the total volume here from 4 to 1 is called as effective swept volume. Then that is given as V1 minus V4. And when you go for this swept volume, so that is V1 minus V3 is the swept volume, and the total volume is from this place to up to V1 is the total volume. So this is the diagram which represents the that is compressor without that is with the clearance volume. So some clearance is provided here. So what is the need for that clearance? So you can see that A, B, C, D. So that is A, B, C, D, which will give the total area of this. You can get the total area of this. So and this process, both the compression as well as expansion is a polytrophic. PV power n is equal to constant, and you can see so two constant pressure process are there. Okay, so it is a spacing between the top of the piston and the valve's head. So why this clearance volume is provided? So you can see that one also here. So it is a spacing between the top of the piston and the valve's head when the piston is at the end of the delivery stroke. So when you go for the good quality machines, they have a clearance of about 6%, but the compressors with clearance of 30 to 35% are generally common. So mostly, so the compressors are provided with 30 to 35% of clearance volume. And what is the reason for this clearance volume? So it gives a mechanical freedom to the moving parts and reduce noise and vibration during operation, then prevent the damage to the moving components. So it prevents damage to the moving components, that is especially to the piston crown. Okay, so this is the reason for that clearance volume. Okay, so then when you go for this process, what are the processes which are involved in these compressors? You can see that an induction process, so then compression process, delivery process, and expansion process. So in case of this induction process, the inlet valve get opens, and here the fresh atmospheric air is induced into this cylinder at a constant pressure and temperature. So you can see here the fresh air is induced into the compressor. This is the start of this compression process. Okay, so the fresh air is induced into the compressor. Okay, at pressure P1 and T1. So the volume of air here induced is VA minus VD. So that is actual air and delivered air. So ideally there is no heat transfer from the air to the surroundings. There is no heat transfer. So Q is here, it is a 0. So in case of compression process, both the valves get closed. So the induced air is compressed according to the polytrophic law, that is PV power N is equal to constant until the pressure and temperature increases to P2 and T2. So here also there are no heat transfer from the air to the surroundings. Then in the delivery process, the exhaust valve get opens. The compressor air is here is delivered out of the cylinder at a constant. So the intake is also at constant pressure process, and the delivery is also at the constant pressure process. There is no heat from the air to the surroundings. Then the expansion process, the piston begins the induction stroke. The compressed air, it occupies the clearance volume, that is VC. So it expands according to the polytrophic law, PV power N is equal to constant until the pressure and temperature they fall to this P1 and T1. So ideally there is no heat transfer from the air to the surroundings. Okay, so you can see here, so this is one of the important factor, so in compressors, so that is volumetric efficiency, which measures the performance of the compressor. Okay, so how much volume is occupied in and how much it is compressed, so is given by this term volumetric efficiency. Okay, so volumetric efficiency is the ratio between free air delivered at standard atmospheric conditions in one delivery stroke. So that is the actual air intake. So what is the actual air intake to the swept volume? So as I told you, you can see this that is PV diagram. So you can see what is the actual amount of air that is sucked in. So it is nothing but the effective swept volume. So that is V1 minus V4 is the effective swept volume. So you can see here, so that is the effective swept volume by this swept volume, that is V1 minus V3. So V1 minus V4 by V1 minus V3 is this V1 minus V3 is nothing but the swept volume. So from this you can arrive an equation for this volumetric efficiency. So that is eta is equal to 1 plus, so instead of K, this is here it is given as K. So you can take as you like K or C, whatever may be, minus K into Rp whole power 1 by N. Okay, so this K, it refers, so the clearance ratio. So that is C is equal to, that is K is equal to Vc divided by Vs. So that is the ratio between clearance volume and the swept volume. Okay, so you can go for, so sometimes you may get this value. So you have to find the value of this efficiency. So you may get the pressure ratio. Okay, so either temperature will be given to you. So in that case, so you have to find the final pressure, and based on that you have to find the value of this Rp, and then you have to find the value of K using this relation, that is clearance volume and this swept volume. So from that you have to find the value of efficiency. Okay, so from this formula, so you can find the value of the efficiency, that is volumetric efficiency. That is the volumetric efficiency. Okay. So you can see here K is the clearance ratio, so that is V3 by V1 minus V3, that is equal to Vc by Vs, so which has a value of around 4 to 10 percentage. Okay. So the greater is the clearance ratio. So we see that clearance ratio K or whatever may be C, K or C. So that is the greater is the clearance ratio Vc divided by Vs, or otherwise you can see in this. So that is V3 divided by V1 minus V3. V3 divided by V1 minus V3. Okay, so the greater is the clearance ratio through a reciprocating compressor, the greater will be the effect of clearance volume. Since the clearance air will expand through the greater volume before the intake condition is reached. So these are all the statements which you may get related to these compressors. Okay, so you have to be thorough with these statements. So the greater is the clearance ratio. So through a reciprocating compressor, what will happen? The greater will be the effect of the clearance volume. Okay, why? What is the reason for that? Because the clearance air will expand through the greater volume before the intake conditions is reached. So that is the reason. So you have to know the statement as well as the reason, because so you are not getting the same questions as that of the previous year. So year by year the questions changes, so it becomes harder and harder. That means the basic concepts has to be thorough with the students. Okay, so only then you can answer the question. So you may not get a straight question, that is by giving all the data and you can answer. That is not at all so possible in especially in GATE exams. Okay. So assuming polytrophic index to be same for both compression and the clearance. So both the compression and the expansion. So you can see here, so that is, so this is with the PV diagram with the clearance. So this is compression 1 to 2 and 3 to 4 is expansion. So we consider both these process so as polytrophic process. So PV power N is equal to constant to be same for both compression and clearance expansion. So that is indicated work per cycle. So this diagram is represented or indicated. So that is why, so we know that if you want to find this area, W is equal to PdV, we know all these things. So the same formula is applied here and we are arriving this formula. Okay, so for polytrophic process, what is the work done? Okay, so W is N by N minus 1, P1, V1. So we know that it is actually V1. So, but here it is the effective swept volume. The volume that is taken in V1 is the total volume. Okay, but what is the amount of air that is sucked in? Is the effective swept volume. The effective swept volume is, so that is the difference between V1 and V4. Okay, so that is V1, instead of V1 you have to substitute as V1 minus V4. So into P2 by P1 whole power N minus 1 by N minus 1. So when you simplify this, you will get the value as N by N minus 1 MA. So that is PV is equal to MRT, the same concept. Okay, so using the gas equation, you are substituting the value and you are finding the indicated work per cycle. So this is the formula for indicated work per cycle. Okay, right. So then we are going for multi-staging. So far we have seen the compressor without clearance and the compressor with clearance, and in both the cases we have seen what is the work done. Okay, so in case of without clearance, so the total volume is considered, V1 is considered. When you go for that is when you go for with clearance, so you can see that V1 minus the effective swept volume is considered, and when you go for this without clearance, the total volume is considered. Okay, so right, now we can go to multi-staging air compressors. There are certain disadvantages to increase the delivery pressure to a higher value. So you may, in a single cylinder, that is air compressor, you may not get that much of high pressure. That suppose if you are in need of high pressure, so you may not able to get such a high pressured compressed air. So that is not possible. So we are going for multi-stage compressors. So one by 1. So the outlet of outlet pressure of one cylinder will be the inlet pressure to the next cylinder, and it continues and it so on. It carries like that. So there are certain disadvantages. So to increase the delivery pressure to a high value, when the delivery pressure is increased to P3, the volume of the fresh air induced is also reduced from VA minus VD to VA dash minus VD dash, and whereas the swept volume Vs, it remains constant. Since the volumetric efficiency is given by eta volumetric is equal to VA minus VD divided by Vs, the volumetric efficiency will decrease with increasing this delivery pressure. Okay, so you can see that. So the volumetric efficiency will decrease. So since the volumetric efficiency is given by this term, and the volumetric and the value, that is the fresh air induced, is reduced from this VA minus VD to VA dash minus VD dash. Okay, so this has been reduced now. Instead of VA minus VD, now it has been, the value is reduced. Since these two are directly proportional to each other, if it has any effect on this numerator side, the same will be on the other side also. Okay, so the efficiency will also reduce. So we are going for multi-staging. So in order to improve the efficiency, we are going for multi-staging. So you can see here, so this situation can be improved by performing this multi-stage compression. What is the reason for multi-stage air compression? So the reason is this. Okay, so these 2 points will give you the reason for that. Okay, so you can see the multi-stage compression process, that is one. So one, then B, then it goes on like this. So it moves on. So you have a low pressure, high pressure cylinder 1 and 2. Okay, so it goes on like this. Okay, so in between that, if you place intercoolers, so that also you can see here. Okay. So now multi-stage compression, you can see the diagram, PV diagram, which represents this multi-stage compression. So after the first stage, the air is passed into a smaller cylinder, then in which further it is compressed to the desired final pressure. The cycle assumes that delivery process of the first stage will be the induction process of the second stage takes place at the same pressure. As I told you, the outlet of the first will be equal to the inlet of the second. Okay, so you can see here, so A, B, then B to B dash. Okay, then you can see B, then B to B dash, then C, then D dash, then C to D dash. Okay, so you can see all these things. So all the process it follows PV power N is equal to constant, that is the polytrophic process. What are the advantages for this? So each cylinder, it works with a lower pressure ratio, so the operational safety of the compressor is improved. Okay, the pressure ratio is minimum. So when you go for single cylinder, the pressure ratio is high. So now we split all those and the pressure ratio is reduced. So for each and every stage, so the pressure ratio is minimum and you are achieving a higher compressed air. So by that you are achieving that higher compressed air. So that is the overall volumetric efficiency, eta V will get increased. So the mass flow rate is also increased as the clearance air expansion is reduced and the effective swept volume of this cylinder is also increased. So you can see here, so in this diagram, so the effective swept volume also increases. Okay. So you can see that single stage compressor, so you can the delivery pressure of up to 5 bar, and 2 stage, so 5 to 35, and 3 stage 35 to 85, and 4 stage it is above or more than this 85 bar. Okay. Compression without this clearance volume. So this is the condition for minimum work done. Okay, so W is, so for minimum work done, so 2n by n minus 1 into P1 V1, P3 by P1 whole power n minus 1 by 2n minus 1. So for this multi-stage compression, you can see here, so it is 1 to 2, then 2 to 3, okay, so then 3 to 4, so it goes on. So that is, so you can see the diagram, one is without intercooling and perfect intercooling. So you can see that for perfect intercooling, so after initial compression in the low pressure cylinder, so we can see the temperature rise and the air is cooled in an intercooler. So the air is cooled in an intercooler back to its original temperature, that is T2 is equal to T1. So where the point 2, you can see the point 2, 1 to 2, it lies on the isothermal through this point 1. So you can see here, so this is the point 2 which lies on this isothermal through point 1. So you can see here, so like this. Okay, so this represents this continuous thick line represents that is polytrophic process, and this thinner line, that is dotted discontinuous line, it represents the isothermal process. So it follows the isothermal process. Okay, so when you go for this intercooling, so now, so this is this line which represents this area represents the low pressure cylinder, and this area represents the high pressure cylinder. Okay, so the intake pressure is P1. So it starts from here and it reaches at this point. So this is the actual volume that is sucked inside the cylinder. Okay, so W minimum will be equal to 2n by n minus 1 into P1 V1 into P3 by P1 whole power n minus 1 by 2n minus 1. So this is the formula for this minimum work done in a multi-stage process. So the next is rotary compressors. So rotary compressors, we have two classifications. One is positive displacement type and the other one is continuous flow compressors. So in positive displacement type, you have root blowers. So you may get a question, root blower is a type of, so maybe it is a positive displacement type. So maybe, so you may get an option like a rotary positive displacement or reciprocating positive displacement. So like that you may get or a centrifugal compressor, you may get option like that. Okay, so this root blowers are this positive displacement, they are rotary types. Okay, so continuous flow, it is classified into centrifugal and axial flow compressors. So now we can see this is centrifugal compressors. So in centrifugal compressors, so they accelerates the velocity of the gases. So that means it increases the kinetic energy. So since velocity comes, so if it increases, Ke also get increases. Okay, which is then converted into pressure as the airflow leaves the volute and enters the discharge pipe. So it deliver much higher flow rates than the positive displacement compressors. So centrifugal compressor, it displays it what is that, it deliver higher flow rate. So it is one of the important point which is related to this centrifugal compressors. And for low pressure ratio, when the ratio is less than 4:1, so you can use these centrifugal compressors. Suppose if you are in need of higher pressure ratios with a larger unit, so you have to prefer axial flow compressors. Okay, so when axial flow compressors are used, so for higher pressure ratios, so with the larger unit, so you have to prefer this axial flow compressors. So it usually operates at speeds greater than 30,000 RPM. So sorry, 3,000 RPM, not 30,000, it is 3,000 RPM. Okay, so the smaller length, contaminated atmospheres, it does not affect this performance of these centrifugal compressors. Okay, so what the main disadvantage is, it's a larger frontal area and lower maximum efficiency. The efficiency is less, so when in this centrifugal compressor, and the frontal area is also maximum. Okay, the velocity encountered in the centrifugal compressor are very large. The velocity is very large. So the total head quantities should be considered. So the velocities are very high. So you have to consider the value of H. So when since the value of V is very high, so the consideration of the head quantity should be there. So while analyzing this centrifugal compressors, so so you consider a horizontal passage of varying area through which air flowing. So you are going to use for this steady flow energy equation to this centrifugal compressors. So when you go like this, so all the other value will become 0. Then you get the remaining term as Cpt plus. So you know that kinetic energy is there. Cp into T plus V square by 2 is equal to constant is the steady flow energy equation for this centrifugal compressors. You can see that centrifugal compressor, so isentropic efficiency for this centrifugal compressor, it is the ratio of isentropic work to the actual work. So or the ratio of isentropic temperature rise to the actual temperature rise. Okay, so you can see that this is the formula and this is the diagram which represents this centrifugal compressor, and this is the form, that is isentropic efficiency. Here it is equal to isentropic work by actual work, which is given by this formula, that is T2 dash minus T1 by T2 minus T1. And during the compression, the work has to be imparted to the impeller, that is it is negative. So when work has to be imparted to the impeller, it is negative. So the energy balance equation around the impeller will be, we know that Cp into T plus this V square by 2 is equal to this value. So we have seen that in this, that is, we can see that it is equal to some constant. It is equal to some constant. So this is the same for the initial and the final conditions. So you can see here, during compression, work has to be imparted to the impeller and the work is negative here. So Q is 0 and here Cp into T1 plus V1 square by 2 plus Q is 0 will be equal to the same for outlet conditions, Cp_T2 plus V2 square by 2, that work done is negative here, W. So the work input is the product of specific heat at constant pressure and the temperature rise. So for both this adiabatic as well as the isentropic process. So here air enters the eye of the impeller at a mean radius Rm with low velocity. So with this low velocity is converted into a higher velocity depending upon the centrifugal action of the impeller. The air moves radially outwards during its movement and it is guided by this impeller vanes. The impellers, what happens to the impeller? What is the function of this impeller here in case of centrifugal compressors? So you can see this is this statement is one of the important statement. So the impellers transfer the energy of the drive to the air, it causing a rise both this static pressure and the temperature and increase in the velocity. So these are the three things which increases in case of this centrifugal compressors because of the impeller. One is static pressure, other one is temperature, and then this velocity. So the work input it equals the rise in the total temperature. So the work input it equals the rise in the total temperature. Okay, so you can see here, that is a pressure, a kinetic energy, you know that it increases, and you can see in practice nearly half of the total pressure is achieved in the impeller and remaining part is achieved in the diffuser. So a statement. So you have to remember this statement. So in case of centrifugal compressor, the total pressure is achieved, that is nearly half of the total pressure is achieved in impeller and the remaining part in the diffuser. So the pressure ratio of 4:1 can be achieved with a single stage, that is centrifugal air compressors, centrifugal compressors. For higher ratio, for multi-stage compressor is used. So here you can see that the entry of the air here the entry of the air is axial. Here the entry of the air is axial and the blades. So what happens to the blades? These are the statements which you have to remember. Okay, so blades must be parallel to the relative velocity of air at inlet and the outlet. So and the impeller blade angle that is beta 1 and beta 2. So at the inlet and the outlet. So the diffuser, what is the condition of the diffuser blade angle? So that should be parallel to the absolute velocity of air from the impeller. And the discharge, if the discharge from the diffuser is circumferential, then you can see the angle at the outlet should be small as possible. So sometimes you may get a statement like this for this centrifugal compressor. This may be larger. So you should know, you have to study this. So then only you know that this statement is wrong if it is given as larger. Okay, so now actually it is very small. So in case of the discharge, if the discharge from the diffuser is circumferential, then the angle at the outlet should be small as possible. Only when there is a smaller angle, so the discharge from the diffuser will be circumferential. It is a condition. These are the formulas, that is work done by the impeller and the power required. So m dot VW2 U2 by 1000. These are the formulas. So that is used for this centrifugal air compressors. That is considering the steady flow at inlet and outlet of the impeller, assuming the heat transfer during the flow through the impeller is 0, then that is adiabatic condition. So you can get the work done, that is equal to Cp into T01 the Rp naught power gamma minus 1 by gamma minus 1. Okay. So the power input to the compressor, it depends upon these conditions. That is mass flow of the air through the compressor, total temperature at the inlet of the compressor, total pressure ratio of the compressor, which depends upon the square of the impeller tip velocity. So you can see here, it depends upon the square of the impeller tip velocity. So the power input to the compressor, it depends upon mass, then total temperature, the temperature at the inlet of the compressor, then the total pressure ratio, which depends upon the square of the impeller tip velocity. Sometimes you may get it is cube of the, that is cube of the impeller, cube of the impeller tip velocity are equal to the impeller tip velocity. So those statements are wrong. Okay, so you will get statement like this. So you have to identify the correct statement. So only when you are thorough with this working function and what are the factors which involve in this, so how the way, that is power, then this velocity, and then work done, so how it has an impact on the blade angle or the impeller on the impellers. So you can see only when you know all these things, so you can identify the exact statements. So this is the formula for isentropic efficiency, and this is a formula for slip, that is U2 minus VW2, that is visual velocity. And the next is the degree of reaction, that is it can be defined as the ratio of this enthalpy drop in the fixed blade, or ratio between the enthalpy drop in the fixed blade and enthalpy drop in each and every stages. So here that is fixed plus moving blade. Okay, so degree of reaction, it can be defined as the ratio of pressure rise in rotor blades to the pressure rise in each and every stages in an axial flow compressors. Okay. So now we can see a problem which is related to this reciprocating air compressor. A single stage reciprocating air compressor, it takes in 1.4 kilogram of air per minute at 1 bar and 17 degrees centigrade. So P1 is given to you, T1 is given, and it delivers at 6 bar, that is P2 is 6 bar. So the compression process follows this law, that is PV power N is equal to constant. So you have to find the value of indicated power input. So indicated IP is equal to W N, that is divided by 60. So this is for, so work done, you know, so the unit is kilojoule per second. So kilojoule per second or kilojoule per minute. So only when you give this in terms of second, so you will get this joule per second is watt. So then you will get the value in this value will be the unit for power. So you have to find when you find the work, then you have to divide by 60, so that you will get the value in terms of kilowatt. Okay. So now you can see that, so what are the things that are given to you? So you have to find the value of indicated power. So we know the formula for indicated power. So based on this, so you have to arrive the equation. So now you know the value of P2 and P1, but we don't know the value of T2 here. So you use this PVT relation. You can see here, so T2 is equal to T1 into P2 by P1 whole power N minus 1 by N. So from this, you can find the value value of T2, so then you substitute the value of T2 at this place, so you can find the value of this W in. When you divide that by 60, so you will get the value, that is 4.43 kilowatt. So you can see here, so this is given in terms of minute, so when you divide by 60, so you will get in terms of minute, that is kilojoule per second, that will be kilowatt. Okay, so so the problems which are related to this reciprocating air compressors, so depends upon the formulas that are used for optimum work condition or for maximum work. So you have to look at the question, you have to read the question thoroughly, and then you have to apply the respective equations. Okay. So the next one is a typical PV diagram for a reciprocating air compressor is shown in this diagram. So it is shown in this diagram. The index for the process is assumed to be N. So okay, so in all the process you have N, right? So then the work done by the piston during the process. So the work done by the piston has to be given. So W, you know, that is P integral dV. So that is the work done. Okay, so now you have to find the work done for this polytrophic process. So first you have to find the work done for the system. So work done for the system is P1 V1 minus P2 V2 divided by N minus 1. Am I right? So this is the work done by this work done by the system. But what is the thing? So that is why I told you to read the question. Work done by the piston. Okay, so that means, so the work done by the piston will be negative of this system work. Okay, so you have one more option also here, you see here, so P1 V1 minus P2 V2 by N minus 1. So immediately what you will do? So you will immediately take this answer. Okay, but that is wrong. Okay, so since it is negative, so this becomes P2 V2 minus P1 V1 by N minus 1. So the answer is 1 by N minus 1 into P2 V2 minus P1 V1. So read the question thoroughly. Okay, so only when you read the question, so you may able to answer, because so that means, so the system work will be, the piston work will be the negative of system work. So should be known to you. Okay, should be known to you. So then, so a simple problem. This is a simple problem, but it carries 2 marks or 1 mark. Okay, so even a mark may so make your life. So a single mark may change your life. Okay, so right. So this. This is the problem. So you can see the solution. Yes, the solution is like this. The answer is D. Okay, so the next one. So a reciprocating compressor has a clearance ratio. It has a, you know that clearance ratio is clearance volume, C is VC by Vs. Right? So if N represents the index of expansion process, the maximum possible pressure ratio obtained during the process. Obtained using the compressor is maximum possible pressure ratio. So eta volumetric is 1 plus C minus C into Rp whole power 1 by N. Right? So now you have to obtain the maximum possible pressure ratio. So if you make this as maximum possible pressure ratio, that means you have to make this minimum. This as minimum. Okay, so if you make this minimum, so the minimum value is nothing but a 0. Right? So if you make this as 0, you can see here. So 1 plus C will be equal to C into Rp whole power 1 by N. Okay, so you can see that, so this can be changed, that is 1 plus C divided by C. This can be, will be equal to Rp whole power 1 by N. So you can see in this, so that is, so you have to make this Rp as maximum. So that 1 plus C minus C into Rp whole power maximum, that is 1 by N. So you bring this Rp max to one side and all the other terms to other side. So you will get the answer as 1 plus C minus C into Rp whole power max, that is 1 by N. So will be equal to 0. So that is 1 plus C. So will be equal to C into Rp whole power 1 by N. So you bring this to this side to this. So that is C to this side. So you are making this Rp, so your maximum value. So when this 1 by N comes to this side, it becomes N. Right, so now you can change this 1 plus C divided by, so 1 by C plus C by C. So if you simplify this, so this becomes 1 by C plus 1 whole power N. Okay, so do you get that option in any of this? 1 plus 1 by C whole power N. 1 plus 1 by C whole power N, yes. So you get the answer, and the answer is D. So this is the way you have to simplify it. The next one, so you can see here, gas turbine plant working on the Joule cycle, it produces 5000 kilowatt of net power. If its work ratio is 50%, the work ratio is given to you. What is the power consumed by the compressor? So this comes under compressor as well as in turbine. Okay, so you may get in the turbine also, and also in here. So in compressors, so you can see the compressor work. So the net work, so we have seen that WT minus WC. So the net work that is given to you is 5000 kilowatt, and then the work ratio. So you have to find the value of this turbine. So that is turbine work. So the work ratio is W net by WT. So the work ratio is 50%. So 0.5. 0.5 is equal to W net by WT. So W net is given to you. The only unknown is WT. So you find the value of WT. Okay, so W net will be equal to WT minus WC. So WT 10,000 and WC is, what is the value for WC? You have to determine, and the total value is 5,000. So it is, the remaining is 10,000 minus this 5,000 will be equal to 5,000 kilowatt. Okay, so this also comes in this, what is that, turbine as also, and also in compressors. Okay, the next one is, which of the following is not an, so you see here, which of the following is not an effect of this reheating? So you can see that, so when you go for reheating, what are all the effects? First thing you should know, when you go for reheating, what are all the effects? Okay, so your work output increases when you go for reheating. But the question here is, so when there is no one which is not an effect of reheating, okay, but contradictory, it is contradicts. So that is, the net work output increases when you go for reheating. Okay, so this answer is wrong. Then turbine work output increases. Yes, turbine work output increases. Okay, so then a change in compressor work. But the effect of reheating is no change in compressor work. Okay, so there is no change in compressor. Scope of regeneration increases, yes, because the turbine exit, so it gives you a higher temperature. Okay, so you will get an higher temperature. So this also right. In case of which of the following is an effect of reheating, so all these comes under this what is that effect of reheating? When there is no reheating, so it is not an effect of reheating, so no change in compressor work. So the answer is C. So the change in compressor work is given to you. So the answer is C. Yes. So you can see the effects of reheating. So from this itself you can get 2 or 3 questions. Okay, so now you got 3 questions. That is the effect of reheating, no change in compressor work, turbine work output, then net work output, scope of regeneration, because turbine exit temperature increases. Okay, so these are all some of the effects of reheating. So no change in compressor work, but here it is given as change in compressor work. Okay, the next one is find the minimum number of stages required when air enters at 1 bar. P1 is given, T1 is given, then delivers at 260 bar. So that is P2 is given. P2 by P1 is given to you. The maximum temperature at the outlet of the compressor is given to you. That is 327 degrees centigrade. T2 is given to you. Take the perfect intercooling between the stages and Y is equal to 1.3. So a formula is there for this to find the minimum number of stages. So P2 by P1 is equal to P3 by P2 is equal to P4 by P3. It goes on. Okay, so when you study the compressors, so you can see here Pn plus 1 by Pn will be equal to K. So Pn plus 1 will be equal to K into P power P suffix n, that is R P. So maybe, so this Pn plus 1 will be equal to K power n. So you can write like this, K power n into P, that is if it is first stage, it is P1. So you can take this formula and you can take this. So that is as Pn plus 1 is equal to K power n into P1. So for perfect intercooling, the inlet temperature for each compressor will be same. So this is the condition for perfect intercooling. Now you got a condition for perfect intercooling, that is the inlet temperature for each compressor will be same, and as we know that pressure ratio will be same for each stage. Okay, so maybe so the pressure ratios, so here it may be P2 by P1, that is 10 by 5, so that is equal to 2. So the other may be 20 by 10, so will be 2. Okay, so you can see here the pressure P3 by P2, P3 by P2. So this is P2 and this one is P1, and now this is P3 and this is P2. So P2 you can see that it remains the same. So P2 20 by 10. So you will get the same value when you go. Then next is what is that, 20. Then P4 is that is 40 by 20. So that is also 2. Okay, P3 is 20 now. So then P4 is 40. So you will get the same ratios. So that pressure ratio will be same for each stage. So for perfect intercooling, so we can write as, so that is we can find the value of n as Pn plus 1 is equal to K power n into P1. So K is so not known to us. So you have to find the value of K, and P2 by P1 is known to you. P2 by P1 is known to you. That is T1 by T2 whole power gamma by gamma minus 1. So for adiabatic compression process, so you got this value. So then, so this is equal to K, that is P2 by P1. That is T1 by T2, so that is given to you. So that is K, so K power n. So solving this equation, that is 260 by 1 is equal to K power n. So you get the value of around 1.85, which is nothing but, so you can go to the nearest value, nearest integer, that is 1.85 is 2. So you can see that the answer is A. And the next one, so rotary type compressors are best for, so rotary type compressors are best for, so you can see that, so they are best for low discharge at low pressures, or otherwise low discharge at low pressure. So you have two options as same. So it is similar. So it is low discharge at low pressures. Okay. So actually this should be high discharge at low pressure. So the answer is large discharge. Okay, so it is B. So that is large discharge at low pressure. Okay, is the answer. So because the rotary compressors are best suited for this large discharge at low pressures. Okay. So the answer is large discharge at a low pressure. So it is not low discharge. So this is wrong. A large discharge, and either you may get this is also wrong. But the pressure is high. But here it is low pressure. So you have to neglect this. So the answer is B. The next one, a centrifugal compressor is suitable for which of the following? So these are all direct questions. So centrifugal compressor is suitable for, so a low pressure ratio. So now only we have seen. So that is centrifugal compressor is suitable for low pressure ratio and high mass flow. So you can see that. So yeah, the typical pressure ratio of a centrifugal compressor is 1.4:1, which is very low. So at low mass flow, the flow channels in the impeller and the diffuser, they are narrow, that the friction loss becomes the main factors, which leads to lower efficiency. So hence they are suitable for high mass flow rate. Okay, so you can see that. So the low pressure ratio is obtained and high mass flow rate, high mass flow. Okay, so next one is the reheat factor for a steam turbine is usually in the range of. So these are all direct questions. Okay, so the reheat factor is 1 to 1.065. So that is the thing. So you have to remember these reheat factor questions. Okay, so you can see that it is the ratio of cumulative heat to the adiabatic drop from the initial condition to the exhaust pressure. Okay, so the value it ranges from 1 to 1.065. So for a centrifugal blower, so the power consumption is proportional to, so the answer is A, that is kW. 1 will be into R2 by R1 whole power 3 will be equal to kW2, that is, so it is cube of, so the answer is A. You can see it is the cubic power of RPM. So these are the questions which are related to the formulas. The next one is, if the isentropic efficiency of a turbine and compressor is given to you, so compressor is given to you, and then the Brayton cycle, and in Brayton cycle is 80%, if turbine work done is given to you and compressor work input is given to you. So find the actual net work done. We know the formula for net work done. So W turbine minus W compressors, but we got the efficiencies of compressor and turbine. So you directly substitute in this formula, you will get the value of this net work done. Okay. And the next one is the indicated diagram shown in the figure. So here it is shown in the figure. So on a compressor, so it shows that the discharge valve, here it shows the discharge valve is leaking into the cylinder during the compression stroke. So you can see that. So the answer is B. So the discharge valve, so the work done on the air delivered is not affected by the clearance volume. So here you can see that from this diagram, so you can easily say that the discharge valve is leaking into the cylinder during this compression stroke. So it is normal nature, this indicated diagram, this is the indicated diagram, and during this compression stroke you can see instead of reaching at this place, it stops here itself. So this is ideal and this one is actual. This is actual. So it stops at this place itself. So that means something has happened during this compression stroke. So you cannot able to answer this because suction, it is suction, and this one is also suction. Suction valve sticking open at the beginning. So that means if it is sticking open at beginning, this is suction. Okay, so something has to be given at this place, but it is not so. So the only answer you can go is discharge valve is leaking into the cylinder during the compression stroke. As I told you earlier, if you are not thorough with the answers, try to eliminate the wrong one. Okay, so from this diagram itself you can eliminate two answers that are given as choices. So you can eliminate these two, and the other one is suction valve sticking open at the beginning of the compression stroke. So it is not given at the beginning, so it is given at the end of this compression stroke. Okay, so during the compression stroke. Okay, so you can easily answer this question, and the option is B for this. Okay, right. The next one, the compressors used in a gas turbine are typically of which type? So you can see that, so there are different basic categories of gas turbine compressors: axial, centrifugal and mixed flow. In case of an axial type, so which is mostly used in the gas turbine, usually a rotary air compressor is used with a gas turbine, and mostly centrifugal compressor or axial compressor is used. Centrifugal or axial compressors are used, so you can answer centrifugal or axial compressors. Okay. The next is, for the same pressure ratio during compression, so compressing in two-stage compressor with perfect intercooling is there. So instead of a single stage compressor, so it is characterized by increase in volumetric efficiency, decrease in work input, decrease in discharge temperature. So which of the statements are correct? So in volumetric efficiency will increase. So when you go for two-stage, yes. Then work input, yes, we are trying to reduce the work input, and then decrease in the discharge temperature, yes, the discharge temperature is reduced. So the answer is, so you go is D, that is all the three are right. So 1, 2 and 3. So now, so we can see a problem, that is the degree of reaction in an axial flow compressor is defined as, we know it is a direct question. So the degree of reaction is defined as the ratio of static enthalpy rise in the, so rotor to static enthalpy rise in the stages. So this is the answer for this. So directly we know the answer, so you can go for it. Okay, so it is the answer is C. So the next one is, air enters the compressor at 1 bar, P1 is given, T1 is given, which is also the state of environment. It leaves at 3.5 bar, and that is P2 and T2 are given, and the velocity is given to you. So velocity is given. So for compressors, so we have studied that, so when the velocity comes, so when the velocity comes, the steady flow energy equation has to be considered. Okay, so neglecting the inlet velocity and potential energy, the isothermal efficiency is, Cp is given to you. So the what is that? So you have to consider this steady flow energy equation. So the WA will be equal to H1 minus H2 minus V2 square by 2. So all the values are known to you here. So you substitute that. So if you can find the value of this isothermal work, so you are in need of the efficiency. Efficiency is WT divided by, and this is WA. So WA is known to you from this equation, and WT is, so integral VdP minus V2 square by 2. So this is known as, this is RT1 into ln of P2 by P1. So everything is known to us. So this can be written, instead of PdV, here it is given as VdP. So that is minus of RT1 into ln of P2 by P1. So you know all these things. So you get the value. So that is 113 kilojoule, so per kilogram. So WT is less than WA. You can see that WT is less than WA. So for compression, isothermal gives the minimum work required. So efficiency is WT divided by WA. You will get the value, that is 113 divided by this 115.7 will give you this value. Okay, that is 97.7%. The next is a three-stage compressor having perfect intercooling in each stage. So it is a three-stage compressor. If the pressure at the end of the third stage is 64 bar, that is P3 is 64 and P1 is 1 bar. So P3 divided by this one, that is Px plus 1 by this one, this value P1 is given to you. Then what will be the pressure at the entry of the second stage? So P1 is given. So this is a three-stage compressor, not P3. So 1, 2, 3, 4. So first stage, second stage, third stage. So 1 to 2, 2 to 3, 3 to 4. So sorry, P4. So P4 is given to you. It is 64 bar, and then P1 and the pressure at the inlet of the compressor P1 is given to you. So for perfect intercooling, we know the equation. So this is the diagram which represents 1 to 2, 3, 4. So P2 by P1 is equal to P3 by P2 is equal to P4 by P3, that is equal to K. So N is the number of stages. Already we know this equation, that is P4 by P1 is equal to the K power N. So N is the number of stages. P4 is known to you, it is 64 divided by 1 is equal to K power, number of stages is 3. So then you can get the value of K as 4. So pressure at the entry of the second stage. In this question itself, you have two questions. That is, one is you can find the value of K, number of stages, using this formula, and the other one is pressure at the exit of the second stage, that is P2. We know that P2 by P1 is equal to the same, that is K, that is P2 by P1 is equal to 4 here. So that is P2 will be equal to 4 bar. So the answer for this one is, it is a 4 bar. Okay. Next one is a single stage air reciprocating compressor has a clearance ratio is given, C is given to you 0.04, and it works under a pressure of 5. The volumetric efficiency of the compressor in percentage. So you have to find the same formula, that is eta is equal to 1 plus C minus C into Rp whole power 1 by N. So that is use the same relation, that is 1 minus, you can see that how this relation comes. So you can take this C out, so minus C into Rp whole power 1 by N. Rp is nothing but P2 divided by P1. The pressure ratio is given to you minus, so you have to get this term plus C, so minus 1. So when you can see here 1, so minus C into minus 1 plus C, then minus C into this Rp whole power 1 by N. So this is simplified here like this. So 1 minus 0.04 into 5, pressure ratio is given to you 1 by 1.4, the minus 1, that is 91.37 percentage. The next one is a multi-stage air compressor with intercooling is to elevate the pressure from 1 bar to 125 bar such that the pressure ratio per stage will not exceed 4. The pressure ratio will not exceed 4. So per stage will not, the required number of stages. So the formula is P, we have seen this formula. So Px plus 1 by Px is equal to Px plus 1 by P1 whole power 1 by N. So use that formula. So this pressure ratio, the question is, you will not exceed the value of 4. So 4 will be equal to, so you get this, that is, it is around 1 bar to 125 bar. So 125, that is 125 divided by 1 will be equal to whole power 1 by N will be equal to this 4. So 125 whole power 1 by N is equal to 4. So take log on both sides. So 1 by N log of this 125 will be equal to log of 4. So then you can find the value of N, that is 3.48 to 3.5 or 4. So number of stages should be a whole value, so it is 4. The next one is a single stage reciprocating air compressor takes in 1 meter cube of air per minute at 1.013 bar and 15 degrees centigrade. So V1 is given, then that value, that P1 is given, T1 is given. So it is a single stage, so P2 is also given, then the N, small n, polytrophic index 1.4, then for the process is then the power required to compress the air. So you have to find the power required to compress. This is the formula for the power, that is the indicated power, N by N minus 1 into M dot into R into T2 minus T1. So you see that, so you have to find the value of M dot, and then T1 is given to you, T2 you have to find. So you can easily find the value of this P using this is a direct question. So you can easily find the value, so m dot, but the only thing is you should know this formula, the indicated power formula, by substituting the given data. So use the formulas according to the data that are given to you. So you get the answer as 4.35 kilowatt. Okay, the next one is air enters a centrifugal compressor at 30 degrees centigrade and leaves at 150 degrees centigrade. Find the isentropic efficiency of the compressor if the pressure ratio is given to you. So air enters a centrifugal compressor. So this is a centrifugal compressor, that is T1 is given to you, and it leaves at what is that, T2 is given to you. So T1 is given and T2 is given, that is equal to Rp whole power gamma minus 1 by gamma. We have seen this formula also. So substitute that, you will get the value of T2. So substitute in the isentropic efficiency, that is T2 S minus T1 divided by T2 minus T1. You will get the value, that is isentropic work by the actual work. So that this is nothing but the change in isentropic temperatures, and this is the change in the actual temperatures. So you will get, all these values. So the only unknown is T2S. So you find this value and you substitute here, you will get the answer for this one. So it is around 75.5%. So the answer is 76%. Okay. Right. The next one is a 3-stage compressor. So it is a 3-stage compressor, reciprocating compressor. It has a suction pressure P1 is given to you and delivery pressure. So 3-stage. So you have 3 stages here, 1, 2, 3, 4. So the delivery pressure of P4 is 32 bar. For minimum work of the compressor, what is the delivery pressure of the first stage? So you have to find the suction. PS is given, PS, PD is the delivery pressure at the last stage. So the pressure ratio is PD by PS whole power 1 by N. So we know this, where N here is the number of stages. So RP here you can say that, so the pressure at the last stage is 32 bar divided by 1.1 whole power 1 by N. This N is the number of stage is 3. You will get the value of RP. So the delivery pressure of the first stage can be given as, so PS into RP. So the value of PS is given to you, that is 1.1 bar at the initial stage, that is the suction pressure of the first stage, and this is the pressure ratio. So you have to remember these two formulas. One is for pressure ratio, PD by PS whole power 1 by N should be known to you, and if you want to find the delivery pressure of the first stage, you can write that it's a product of this suction pressure at the first stage and the pressure ratio. These two should be known to you, then only you can find the value of this delivery pressure. It is 3.38 bar. So two simple formulas has to be known to you. So you can easily work out the problem with the help of the formulas that are known to you. Okay. The next one is a reciprocating compressor working between the pressure limit of 1 bar and 10 bar. So the pressure limits are given to you, the bore and the stroke. Okay, so this is to find the bore. If bore and stroke are given to you, then it is used to find the value of this Vs. So then if the clearance volume is for Vc is also given to you, find the volumetric efficiency. So we know that eta is equal to 1 plus C minus C into Rp whole power 1 by N. So this C is nothing but Vc by Vs. So if you find these two values, so you know this, so use the formula for Vs, so then you can easily substitute here, you can find the efficiency, right? So the same Vs is pi by 4 d square into L. So you know clearance wall ratio is known to you, so that is for Vc by Vs. So you can find the value of C, substitute in this equation, so you get the volumetric efficiency, which is 75.84, that is 76. So option is CA. So the next problem. So in axial flow compressor, air enters and relieves the stage axially. Find the degree of reaction if the whirl component of air leaving the rotor is 1/3 of the mean peripheral velocity of the rotor blades. You can see that the mean, so this is the degree of reaction, the formula for degree of reaction, that is 1 minus the whirl velocity at the second stage, and the velocity at the second stage will be is equal to, so that a hint is given to you, leaving the rotor is 1/3 of the mean peripheral velocity. So that is equal to 1/3. So when you substitute the value of R is equal to 1 minus 1/6, you will get the value of 5/6, which is nothing but R is equal to 0.83. So the value is 0.83. So the answer is 0.83. Okay. So the mean is given to you. So you can see in that problem, so if the mean is given to you, it becomes 1/3, that means 1/6. So you will get the value as 1 minus 1/6, so equal to 5/6, that is 0.83, that are 83%. So then air enters the centrifugal compressor at 310 Kelvin. The slip factor and the work factor are 0.92 and 1.04 respectively. If impeller external diameter is given to you, which is running at 12,000 RPM, find the temperature of air at the outlet. So you can see the temperature of air at the outlet, so that is T2. T2 is the temperature of air at outlet. The actual power of the compressor is given by Cp into T2 minus T1, so which is equal to pi s into pi W. So into this velocity square. So you find all this. So one is pi s, you can see, you can look at this, pi s is given, and pi W, that is 1.04. Pi W is also given. So those two are the slip factor and the work factor. They are given to you, and U2 you have to find the value. So that is, what is the U2 is pi d n by 60, right? Pi d n by 60, d is given and n is also given to you. You can easily find the value of U2. Substitute all the others, so you can get the value of the only unknown, that is T2. You can find the value of T2, which is 521.42 kilowatt. So the thing is, the power for the compressor equation should be known to you. That is Cp into T2 minus T1. So you can equate this with this product of this slip factor and the whirl factor with the square of the velocity. So if you know this equation, so directly you can substitute. You know U is pi d n by 60 is known to you. Okay, T1 is given to you, Cp is known to you. So directly you can substitute in this equation and find it. So these are all direct question type. Okay. Okay, the next one, in a reciprocating compressor, so as the pressure ratio increases, so delivery temperature will also increase. Okay, so you can see that that is the question, that is, with increase in pressure ratio, so delivery temperature will also increase. So when you increase this will also increase. So this is a basic concept, so you can easily answer the question, and the option is A here. So formula, so direct PVT relation, based on the PVT relation. The next is the ratio of pressure rise in rotor blades to the pressure rise in stages in axial flow compressor is defined as, so degree of reaction. So this is a direct question. Okay, the answer is B. The next is the maximum and minimum temperatures are given to you in an Otto cycle. The expansion ratio is given. Then the ratio of compressor work to expansion work. So compressor work to the expansion. This is already we have seen. So the ratio of compressor work to expansion work. So this is based on this is a PV diagram. So already we have seen this. So then an axial compressor operates such that it has an inlet and exit, a total temperature of 300 Kelvin and 430 Kelvin respectively. The isentropic efficiency of the compressor is given to you, and the ratio of specific heat Cp and Cv is 1.4. What is the total pressure ratio across the compressor? Okay, so the total pressure ratio is that is T2 by T1 whole power gamma by gamma minus 1. So you have to find the value of T2 and T1 is given to you. So T2 should be found out from the relation that is given to you. So we know that efficiency of the compressor is, so can be given like this. So that is 0.85, the efficiency is given, T2 is not known, T1 is given to you. And one more thing is, you can see that exit total temperature of 300 Kelvin and 430 Kelvin is given to you. So T3, the higher temperature is given, that is 430 Kelvin is given to you. So you have to find the value of this, and here it is 300 Kelvin. So T3 is known to you. So you substitute here, the only unknown will be T2, find the value of T2 and substitute in this, that is equation, that is T2 by T1 whole power, this bring this one to this side, this is PVT relation, gamma by gamma minus 1. So you can easily find the value of T2 by T1. This is nothing but the pressure ratio, that is R suffix P is equal to 410.5 divided by 300. So you can get the value, the pressure ratio is 3. So now you can see a problem, that is PV diagram of a typical reciprocating air compressor is given to you. So which of the following option represents the corresponding TS diagram? So you may get questions like this. Okay, so assume the process 1 to 2 and 3 to 4 as 1 to 2 and 3 to 4 as reversible adiabatic. So you can look at the other process, that is TS diagram for B, C and D as well as A. So 1 to 2 and 1 to 2 and 3 to 4. So you can see that, so the heat transfer, when you go for the heat transfer, so no heat transfer in any of the process. So the area below the each curve on TS diagram, it should be 0. Okay, so you can see that in process 2 to 3, that is in process 2 to 3, so air is simply discharged into the delivery pipe without change in pressure, temperature and specific volume. And the entropy is also a property which should not change. So this is the reason. The answer is A, but here area under PV diagram and TS diagram need not be matched because this is not a closed cycle. And that is the mass of fluid in each process is not same. So as there is no heat transfer in any of the process, so that is area below each curve on TS diagram must be 0. Area below this should be on this TS diagram should be 0. So in all these cases it is not so. So the area here it is 0. So the option is A. Okay, so 1 to 2 and 3 and 4, so the area that is there must not be heat transfer occurs. So the area is 0 and the option is A. Okay, so you have to be thorough with the process which involved in this, so and you have to consider other properties also. Okay. The next one is the suction and delivery pressure in a two-stage reciprocating compressor with ideal intercooling is 1.2 bar and 38 bar respectively. What is the value of intercooler pressure? So intercooler is, so you know that P2 is equal to root of P1 into P3. So those two are given to you, 1.2 into 38 you will get the value. So a direct question. Okay, the answer is 6.75 bar. The option is A. The next is isothermal compression, though must efficient but it's not practical. Practically it is not viable. Why? Because so the compressor, you can see that the compressor has to run at very slow speed. So you have to maintain it, since it is an isothermal process, so that you have to maintain the temperature constant. So you have to run the compressor in a slow speed to achieve that T is equal to C. So that is temperature is equal to constant. So the answer is B. Okay, so you can go for the answer, it is B, because we have to go for the low travel, so slow travel of that piston. So you have to maintain that yes, temperature is constant. Okay, the next one is a gas turbine cycle having a turbine output 200 kilowatt and the overall efficiency is given to you. Mass of the fuel consumption is given, that is MF, then CV is given to you. So these two are given for finding the value of heat supplied. Okay, so you are going to find the value of work input to the compressor. So if you find the net work done, you can easily find the net work to the compressor. Okay, W net is equal to WT minus WC. So from that you can, if you know WT and W net, you can easily find the value of WC, right? So this is the data that are given. Based on the data, so you use the formula for heat supplied, mass fuel into, that is the mass of the fuel into calorific value CV. So you can get the value, and efficiency is net work output by heat supplied. From that you can find the value of the net work done. If you know the net work done, so the turbine work minus compressor work is the net work. So turbine work is given to you, so you can easily find the value of the compressor work, which is 50 kilowatt. Okay, so 50 kilowatt A is the option. Okay. The next one is, in gas turbine, intercooler is placed. So where the intercooler is placed? So that it is placed between the low pressure compressor and high pressure compressor. Am I right or not? So you have to be thorough with that. So the answer is B. Okay, so you have to be thorough with the position of the high pressure turbine, low pressure turbine and compressors. Okay, then combustion chamber where it is kept. So you have to know all these things. So in a cycle, whatever may be the cycle, so you have to know all these things. The next one is, so determine the minimum number of stages that are required in an air compressor in which air enters at a pressure of 1 bar and the temperature at 27 degrees centigrade and delivers at 81 bar. The maximum discharge temperature is given to you, and considering the polytrophic index 1.25, assuming perfect and optimum intercooling between the stages. So optimum intercooling is there. So you can see that the initial pressure is given and the final pressure is given. So this is the formula, that is PF by, we have seen this formula, that is Px plus 1 by Px. So that is equal to Px plus 1 by Px whole power n, that is equal to, using that formula, so you substitute the value and find. So from that you can easily find the value of, this is 81 is equal to 3 power n. So from this you can easily find the value of n. So 3 power n, so that is equal to 81. So 3 into 3 into 3 into 3 is 81, 9 81. So 3 power 4 is the answer. So n is equal to 4. So the number of stages for this is equal to 4. So using the same formulas for, if it is stages, so Px plus 1 by Px. So use that formula to find the value of, is equal to K power n. So use that formula to find the value of that n. Or if you are in need of K, so you determine, if the number of stages are known to you, you determine the value of K. So that is the pressure ratios. Okay. The next one is, the compressor of a gas turbine plant is given to you, gas turbine plant operating on a Brayton cycle. So with the overall compression ratio is given to you, and it is a two-stage compression process. The intercooling is used to cool the air coming out from the first stage to the inlet temperature of the first stage before its entry to the second stage. So air enters the compressor at 300 Kelvin and 100 kilopascal. So T1 and P1 are given to you. If the properties of gas are constant, the intercooling pressure for minimum compressor work. So the intercooling pressure P2 is equal to root of P1 and P3. So P1 and P3 has to be determined. So for perfect intercooling, we know that P2 is equal to root of P1, P3. So from that, if you know this value, that is P1 and P3, so you can easily find out the value of P2, that is 244.9 kilopascal. So this is what is that? P2 is equal to root of P1, P3. So should be known to you. So to find the intermediate temperatures, intermediate pressures, sorry. Consider the following statement for single stage reciprocating compressors. So isothermal process is the most desirable process for compression. Yes, now only we have seen, but why it is not possible? Practically, why it is not possible? Because of this slow movement, you have to maintain, and that is the movement of the piston should be very slow. So, but you can achieve a very large, that is a most desirable process for compression. Yes, okay. So the first one is okay. Then the size of the clearance volume provided in the compressor has no effect on the work done per kg of air delivered. Yes, the volumetric efficiency of the compressor decreases with increasing pressure. Yes. Okay, so all these statements are right. So the option is D, that is 1, 2 and 3 are right. Okay, the next one. So in a 3-stage compressor, if the pressure at the entry of the first and third stage are 1 bar and 16 bar, so then delivery pressure, directly you can use the formula for this. So P2 by P1, P3 by P2, P4 by P3. So from this you obtain that formula, that is P2 square is equal to this P1 into P3. So P2 is equal to root of P1 into P3. So P1 and P3 are given to you. So you find the value of the intermediate pressure. So that is P3 by P2 will be equal to P4 by P3. So from that you find the value of P4. So you know that P2 by P1 is equal to P3 by P2 is equal to P4 by P3, that is equal to the pressure ratios. Am I right? So now you can use this P3 by P2 is equal to P4 by P3. So using that relation, since you know the value of P3 and P2, so you can easily find the value of the pressure at the end of the third stage. So that is P4 is equal to 256 by 4, that is 64 bar. So the option is C. So this is a direct question. So simply you are going to use this equation and you are going to find the unknown. So P2 is not known to you. P2 is, since it is an intercooling process, P2 is equal to root of P1, P3. So these two are given to you, P1 and P3 are given to you. So now you have to use the formulas according to the given data. Okay, so based on that only, so you can find the answer. It is 64 bar. So the next one is a refrigerant compressor of 50 mm bore and stroke is given to you. So at a speed is N is also given, and then the condensing and the evaporator pressure limits are given to you. C is given to you. Polytrophic index, that is N is given to you, specific volume is given. So the mass flow rate has to be determined. So the mass flow rate can be determined with the help of this formula, that is MF into V1 is equal to pi by 4 D square L into N by 60 into volumetric efficiency. This is a formula, direct formula. So when with for using this V1, so everything is known to you. So you know the volumetric efficiency, that is 1 plus C minus C into Rp whole power 1 by N. So use this formula, find the volumetric efficiency, substitute here. All the other data are known to you. Okay, D, L, then N, and then speed is known to you, divided by 60 into. So directly you can substitute in that, you can get the value of this MF 0.0, what is that? 1327. So it is 0.01. The answer is B. So 0.01327 kilogram per second. The next is root blower is an example of. So it is an example of a rotary positive displacement compressor. Okay, so it is a rotary type, it is a positive displacement type. So rotary positive displacement compressor. So direct question. So you can see here rotary, so it is a positive displacement. This is a classification of that. So rotary, so lobe type, screw type, vane type, so scroll type, so lobe type, so comes under this, so root blower. Okay, so you have two lobes inside it, so that will rotate, so that comes under, so lobe type, so rotary positive displacement. So no classification should also be known to you. So you see here. So the discharge pressure of the compressor in the refrigeration system goes up due to the, what is that? So due to the formation, that is you can see that 1 plus C minus C into Rp whole power 1 by N. So by increasing the pressure ratio, so the what happens to the volumetric efficiency? So it lowers the volumetric efficiency, lowers. So lower volumetric efficiency of the compressor. Okay. The next one. So you can see that which one of the following statements is correct? So in reciprocating compressors, so one should aim at compressing the air. So now only we have seen. So you should aim at isothermally. So because that even though that is not possible, the question is one should aim at compressing the air isothermally. So due to minimum work, so the input required is isothermal compression. So it is the ideal process. So the answer is C here. Okay, so that is isothermal process. So the flow in the vaneless space between the impeller exit and the diffuser inlet of a centrifugal compressor can be assumed as, so you can see here it should be logarithmic spiral. It should be, so this is a direct question, so it should be logarithmic spiral. So the answer, the explanation is also given here, it should be logarithmic spiral. The next one is reciprocating compressors are provided with, so it should be provided with a simple disc plate valve. Simple disc plate valve. It should be simple disc plate valve. So you can, the direct question, so the answer is A here. Okay, the next one is, so you can see the type of compressor valve used is plate type, so the answer is A. So next one is in a centrifugal compressor, the highest Mach number leading to shock wave in the fluid, it occurs at, so the answer is B, that is after diffuser outlet, so radius, Mach number is highest leading to the shock waves, so the diffuser outlet radius. So diffuser outlet radius, this is also a direct question. So for a multi-stage compressor, the polytrophic efficiency is, so the polytrophic efficiency, you can see that it is defined as isentropic efficiency of an elemental stage of the compressor which is constant throughout the whole process. So it is constant throughout the whole process. The answer is C. Okay. The next one is, which one of the following types of the compressors is mostly used for supercharging this IC engines? It is centrifugal compressor. So now only we have seen that it is centrifugal compressors. So you can, so this is the explanation of that. So next one is, so you can see the next one. So that is in a 3-stage air compressor, the inlet pressure is P1 and the discharge pressure is given to you P4 and the intermediate pressure is P2, that is P2 is lesser than P3. The total pressure ratio of the compressor is 10 and the pressure ratios of the stages are equal. If P1 is equal to 100 kilopascal, the value for the pressure P3 is, what is the value of pressure P3? So we know this, so now only we have seen this pressure ratio. So P4 by P1 is given to you, that is 10. So then P4 divided by P1 is 100. Then P1 is 100 is given to you. P4 will be around 1000 kilopascal. So P4 by P3, this is a 3-stage compressor. P4 by P3 whole power 3 is equal to 10. So then 1000 cube divided by 10 is equal to P3 cube. So from this you can find the value of P3. The value of P3 is 464.158 kilopascal. So the relation for this problem is, you have to use these two pressure equations and from that you arrive this P4 by P3 whole power 3. So this is the number of stages, that is equal to 10. So from this you can easily find the value of the unknown, that is P3, which is 464.158 kilopascal. So the answer is A. The answer is A. So thank you. So with this I have completed all the lectures. So that is the lectures related to internal combustion engines and power engineering. So in internal combustion engines we have seen Otto cycle, diesel cycle and dual cycle and the performance of IC engines. And in case of this power engineering we have seen Rankine cycle, Brayton cycle, and then compressors. So with all these 5 lectures, you will get, I think you will get around 6 to 8 marks in GATE exams. So be thorough with all those, and not only the problems that are worked out in these lectures, but also try to work out different types of problems. So mostly you will get a problematic type. So you try to work out the problems which are really, especially in thermal sciences. So you try to work out different problems. So you try to get many questions and work out all those questions. So and moreover, so I thank all the students of government and government aided engineering colleges, and apart from that, I once again I request all the students to work out the problems which are problems, and also the theoretical concepts which are behind internal combustion engines and power engineering, because you may get statement type questions also. So please concentrate on all these things. So and I also thank the students of various colleges, various engineering colleges who watch these lectures, lecture series for this GATE 2021. And at this time I thank our Commissioner of Technical Education for giving me this opportunity, and also I thank our principal Dr. P. Thamare Madam for giving such an opportunity to conduct these kind of video lectures. So once again I thank you, and once again I request all the students so to concentrate on the statement type questions as well as the problematic type questions for this, especially for this thermal sciences. So thank you one and all. So hard work always pays. Thank you.